let's look at this problem. Any subset of V containing a linearly dependent set is linearly dependent. So if I shrink a linearly dependent set, yeah, any subset of V containing a linearly dependent set. So if I enlarge a linearly dependent set, it remains linearly dependent. Yeah. So when do I say a set is linearly dependent? If there is a non-trivial linear combination of non-zero vectors which produces the zero vector, then that set of vectors is called linearly dependent. So if I have a set which is linearly dependent and I enlarge the set, then the same relation will also hold in the larger set. So a superset of a linearly dependent set is linearly dependent. Similarly, a subset of linearly independent set is also linearly independent. Okay, you can see from the definition. Yeah. So if I shrink a linearly independent set, it remains linearly independent. But if I enlarge a linearly dependent set, it remains linearly dependent. S is linearly dependent if and only if 0 belongs to S or a vector in S is a linear combination of other vectors. So if I have linearly dependent set, and suppose if 0 belongs to S, certainly 0 vector times a non-zero scalar produces 0 vector. Yeah. So as soon as a set contains the 0 vector, it is automatically linearly dependent because 0 vector times a non-zero scalar produces the 0 vector. So if the given set doesn't have the 0 vector and it is still linearly dependent, which means I have a linear combination, non-trivial linear combination of vectors which produces the 0 vector. So suppose I had 3 vectors u, v, and w, and I have a non-trivial linear combination of these vectors produces the 0 vector. And non-trivial means one of these vectors is non-zero. That means suppose alpha is not 0. This means that u can be written as minus beta over alpha, v minus gamma over alpha, w. So therefore u belongs to linear span of v and w. Yeah. So whenever I have a linearly dependent set of vectors, then one of the vectors among those is in the linear span of the remaining vectors. Okay. So therefore, this means that the linear span of u, v, w is same as linear span of v, w. Yeah. Linear w are contained in the set of linear combinations of but u and u is a linear combination of v and w, then the linear span of u is same linear span of v and w, and therefore this sub can be realized as linear span of a smaller set. Yeah, we started with 3 vectors, but if these 3 vectors are linearly dependent, then I can realize this linear span of 3 vectors as linear span of 2 vectors. Okay, so we have found a better, smaller subset whose linear span is the same vector space. Yeah. So a set is linearly dependent if and only if either 0 belongs to S or a vector in S is a linear combination of other vectors. You can prove the converse also very easily. Okay. Now let's consider the vector space area. Focus on area. Then we know that if I take the standard basic column vectors, n of them, e1, e2, en, then S is linearly independent because yeah. These n vectors, e1 up to en, they are linearly independent. This vector, because of the structure of e1, e2, en, this vector is nothing but the column vector alpha 1, alpha 2, alpha n. This equal to 0 if and only if each alpha I is 0. Yeah, each alpha is 0. So that says that e1 up to en are linear dependent. I mean, they are linearly independent. Okay. Let's look at another example. Let S denote the subset of R4 consisting of the following row vectors. Yeah, this is my row vector, which is analog of E1. This is E1 transpose. This is E1 plus E2 transpose. This is E1 plus E3, E2 plus E3 transpose. And this is the transpose of sum of the 4 basic column vectors. Yeah, right. So I have these row vectors, and let's look at the subset. These are 4 of them. R4 is linear combination. It is linear span of 4 basic column vectors. Here are these 4 vectors. I think of R4 now as linear span of row vectors. Okay, let's look at these 4 row vectors. Let's see that these are linearly independent. Okay, how to see that they are linearly independent? So to show that a set of vectors is linearly dependent or independent, I have to take a linear combination. And if I take a linear combination which produces the 0 vector, and that implies that the scalars involved in that linear combination are 0, then that set will be linearly independent. Otherwise, it will be linearly dependent. Okay, so I have to take an arbitrary linear combination of these. Yeah. So alpha 1 times first vector, alpha times second vector, alpha third vector. Suppose it is 0 vector. Simplify this and this on the sum of 1 plus alpha 3 plus alpha 4. That must be 0. Left is alpha 2 plus alpha 3 plus alpha 4. Now go back by back substitution. Alpha 4 is 0. Alpha 3 plus alpha 4 is 0. That says alpha 3 is 0. Look at alpha 2 plus alpha 2. So I took an arbitrary linear combination of these 4 vectors, and which produces the 0 vector. And then I proved that all the coefficients are 0. And therefore, this set is linearly independent. Yeah. Okay. So testing whether a finite set is linearly dependent or independent actually amounts to solving a homogeneous system of linear equations. So we had these 4 vectors. We wanted to test whether these are linearly independent. And then it gave rise to these linear equations 1, 2, 3, 4. 4 homogeneous linear equations. We solved them by back substitution. If it was not so easy to see the solution, then I set up a system of linear equations, find the coefficient matrix, make the augmented matrix, apply row operation using Gauss elimination method, find all the solutions. Okay, so testing whether given set of vectors in are linearly dependent or independent amounts to solving a system of homogeneous linear equations. Okay, yeah. Now let's look at a different kind of vector space. Look at the vector space from R to R. Yeah. Look at all continuous function, real valued continuous function from R to R. And we saw last time that this is a vector space under addition. If I have 2 functions, f and g, which are from R to R, I can simply by this formula that you are used to from calculus. I can take a scalar and take a function. Then alpha f is a function which is defined like this: alpha times f of x. So this vector space of functions from R to R, which are continuous, yeah, this can have, this is actually, we will see, it cannot be a finite dimensional vector space. It cannot be written as a linear span of finitely many continuous functions. Okay, there are all kinds of continuous functions, and finitely many continuous functions cannot give rise to all continuous functions by taking their linear combinations. Okay, look at this set. I have one. This is a constant function, cosine square t, sine square t. These are 3 continuous functions, yeah, from R to R. Let us see whether they are linearly dependent or independent. Yeah. So you all know this relation: cosine square t plus sine square t minus 1 equal to 0. So here is a linear combination of these 3 functions. It's a non-trivial linear combination because the coefficients are 1, 1, minus 1. Yeah. We have a non-trivial linear combination of these 3 functions which produces the 0 function. This left-hand side is zero function because of the trigonometric identity. So these three functions are linearly dependent. Okay, yeah. Now let me produce an infinite set of linearly independent set. Infinite linearly independent set. Okay, we will see later. You cannot do that in Rn. And cannot finite sets which are like and after that it involves exponential function alpha 1 is less than alpha. I could take take any n. Just look at the space of all continuous functions. This is my vector space. Okay, in this vector space, I want to produce infinite set of linearly independent functions. Okay? Here it is. Yeah. So let's look at e to the power alpha to the power alpha 2x e to the alpha n. Yeah. E2x, E3x, and so on. Look at all these continuous functions. Okay. And truncate. E alpha x. So these are n continuous functions. In fact, they are much more than continuous. They are infinitely often differentiable. So that this is a linearly independent set. I can take n real alpha to power alpha nx, and let us show that they are linear. So to show that these are linearly independent, I must show that no linear combination of non-trivial linear combination of them produces the zero function. So take a linear combination, but we will apply induction. So take n equal to 1. When we have n equal to 1, I have e to the power alpha 1x, and suppose that beta times e to the power alpha nx equal to 0. But we know that this exponential function is never 0. Yeah. So I can divide by e to the power alpha 1x for any x and get beta equal to 0. So this actually is true in general. A non-zero vector in any vector space is linearly independent. But in this case, our non-zero vector is this exponential function, and we have shown that it is linearly independent by itself. So this statement that the set E alpha 1x, E alpha 2x, E alpha nx is linearly independent has been proved for n equal to 1. Now I assume this fact for any n minus 1. Assume the assertion is true for n minus 1, and we will prove it for n. So take this n exponential functions and take this linear combination where coefficients are beta 1, beta n, and this is produces the zero function. Then I want to show that each beta I is 0 for all I. Yeah. So if I have this linear combination of E alpha 1x, E alpha nx, producing the zero function, I want to prove that all the betas are equal to 0. Somehow we have to reduce this equation to an equation which has n minus 1 function so that we can use our induction hypothesis. Okay. So, but now use this fact that alpha n is bigger than alpha 1, alpha 2, alpha n minus 1. So this equation I can multiply. Okay, I can multiply this equation by e to, I can divide this equation or multiply this equation by e to the power minus alpha nx. This is also a function. See, if this is the zero function, I can multiply by this function on the both the sides. I still get this zero function, but then I get this relation. And this last function, okay, alpha n minus alpha n, that is equal to 1. So we just get e beta 1 e to the power alpha 1 minus alpha n x and so on. And the last one is beta n. Okay, the last one is beta n. But now I can let x approach to infinity. This is a function of x. Yeah, it's a continuous function of x which produces this zero function. So if I take x approaching to infinity on both the sides, I should get this zero function. But when I let x approach to infinity, then this is a negative real number, and this is zero. Okay, so when x is approaching to infinity, this function is mapping to zero. Okay, so in this relation, I will get only beta n. When I let x approach to infinity, the limit of the left-hand side function is just beta n. The limit of right-hand function is 0, and therefore beta n is 0. So I can put beta n equal to 0 here. Yeah. So I started with this linear combination of n exponential functions by dividing by e to the power alpha n x, and then taking the limit. I approve that beta n equal to 0, substitute beta n equal to 0, then I get a relation between n minus 1 exponential function. But by induction hypothesis, then if a linear combination of n minus 1 exponential function is 0, then those are linearly independent. So all the betas are 0. Once all the betas are 0, I go back and substitute into this. I get beta n e to the power alpha n x equal to 0, and that forces beta n equal to 0. Okay. Yeah. So therefore, I have proved that if I take any distinct real numbers, alpha 1, alpha 2, alpha n, then construct the exponential functions e to the power alpha n x, e to the power alpha 2x, etc., then these distinct exponential functions are linearly independent. So the vector space of all continuous functions has arbitrarily large linearly independent set of functions. Yeah, this is how a vector space of continuous function is different from a n-dimensional Euclidean space Rn. We will see that n-dimensional Euclidean space Rn cannot have infinitely many linearly independent vectors, but the function space of continuous functions can have infinitely many linearly independent functions. Okay, yeah. So let's now look at the vector space of all polynomials. No condition on the degree. Just take all polynomials, real polynomials. Coefficients are real numbers. We could also consider polynomials where the coefficients are complex numbers. Yeah, same statement will hold. So in this, every polynomial is actually a real linear combination. Real polynomial is a real linear combination of 1, t square, etc. These are monomials. So every polynomial is a unique linear combination of these monomials, 1 beta. So in this space, let us see that if I take these monomials t to the n1, t to the n2, t to the nr, where the powers are distinct, then they are linearly independent. Okay. So take a linear combination which produces 0. I want to prove that alpha 1 is 0, alpha 2 is 0, alpha r is 0. And this earlier we multiplied by e to the power minus alpha n x and took the limit. But now we can differentiate. Okay, we can differentiate. So if I differentiate, say nr times, then these things will go to 0 if I differentiate nr times, and this alpha r will be multiplied by some number, and that function will only survive, and that will say alpha r is 0. So differentiate this relation on both sides n1 times, I will get, and then put t equal to 0, I will get alpha 1 equal to 0, and continue this way. Okay. Or you can differentiate nr times, and then you will get alpha r equal to 0. Then differentiate nr minus 1 times, and substitute that will give me other coefficients to be 0. So distinct monomials, t to the n1, t to the n2, t to the nr, these distinct monomials are linearly independent in the vector space of all real polynomials. So the vector space of all real polynomials and vector space of all continuous functions, they have this common property that there is no bound on the size of linearly independent sets. There is no bound. Okay. And so they differ from ordinary Euclidean space with this property that in ordinary Euclidean space, you cannot have infinite set of linearly independent vectors. There will be a bound. We want to show that. Okay, so that is done by introducing what is called basis and dimensions. Vector space comprised a linear span of several sets. Okay, we have seen that several sets of. So if my vector space is linear span of say E1 and E1 plus E2, then also linear span of E1, E2, E2, E1 plus E2, or 2E1. You can always okay, linear span of S is equal to V, and T is a subset of V. Then linear span of S union T is also V. Okay, so I can enlarge a given set and still get the same vector space. But in practice, we want to take smallest set whose linear span is a given space. Yeah. So vector space can be realized sizes. Yeah. Study properties of smallest sets whose linear span is a given value. Yeah. Yeah. So let me first express in words what is a basis. So a subset is a basis of a vector space if elements of S are linearly independent and the vector space is linear span of that. It's a fundamental. A subset of a vector space is called a basis of a vector space. Elements are linearly independent. That means whenever of elements of S produces a zero vector, then it's a trivial linear combination. And the whole space is linear span of the given set. Yeah? Whole space is linear span of the given. So, finite basis for a vector space in linear span of a finite set, we will say the vector space is finite dimensional, otherwise is called infinite dimensional. So you can expect that the vector space of all real polynomials will be infinite dimensional. Because if I take finitely many polynomials, they have bounded degree. There's an upper bound on the degree. So I can't get polynomials of higher degree as linear combinations of polynomials of lower degree. So the vector space of all real polynomials is obviously infinite dimensional. But a finite set of polynomials, if I take linear combinations, then there's a upper bound on the linear combinations of a finite set of polynomials. So the real vector space of all real polynomials is actually infinite dimension. Okay.